A Lenz Law free transformer. This is an extract from a document dated January 2014 by an anonymous author whose ID is Jack No Skills. He says, this short paper describes a simple method how to build a Lenz Law free resonant transformer. Lenz Law is not violated, but it is used to create more efficient transformer. Without Lenz Law the setup could not work. First, some simple tests are presented which forms foundation of the device. Then, based on the results of these tests, I built the transformer which confirmed my test results. It is important to understand the method as that will give you understanding. When you understand it, you can build it using different components than I used. The effect of capacitors in resonant LC circuits. The capacitor's value in a parallel resonant LC circuit controls the attenuation level of band stop filter. A low value of C makes the resonant area smaller and attenuation steeper. A high value of C makes the resonant area wider and the attenuation level lower. When investigating resonant effects, it is wise to start with a high value of C. I used 440 nanofarads to 2000 nanofarads. In any series resonant LC circuit, the frequency response has a notch at the resonant frequency. The frequency response is the opposite of that in a parallel LC circuit. To get maximum effect, it is therefore best to have high attenuation level at a primary parallel LC circuit, low C, and a high amplification level at a secondary LC circuit, also low C. The Q factor is the inductive reactance of a coil divided by its DC resistance. The Q factor determines the resonant rise in a resonant circuit, and so the higher the Q factor is, the higher the power output will be. In a coil, the DC resistance can be minimized using thicker wire and fewer turns. Inductive reactance can be maximized using a higher resonant frequency, which is controlled by the L and C components of the circuit. Smaller L and C values produce an increased resonant frequency. There is plenty of information about the Q factor on the web. I just wanted to put a short introduction to Q factor here so that you will understand that a high Q resonant LC circuit can be dangerous. Two kinds of inductances. Any simple helical coil wound on a core affects only another helical coil which has been wound underneath it or on top of it. If two coils are placed beside each other, there is little interaction between them. Let's call this the local inductance field. A coil wound on a closed-loop core affects any coil on that same core, and the coil also has a much higher inductance than an air core coil. Does this mean that the local field disappears? No, it doesn't. This effect can be used to make a simple over-unity device. 3. Testing of closed-loop cores. I used E-shaped parts from low-power, laminated iron transformers and put those E parts together. I used a primary coil of very high inductance and fed AC through it. The E plates snapped together and stayed that way even after power was disconnected. I tried several times, sometimes the force was strong and sometimes they did not stick together at all. The strength clearly depended on the input AC waveform. When I separated the E plates, they no longer stayed together, so something was interrupted in the core. While the cores were fixed together, they did not have any external magnetic effects and another piece of iron would not stick to the core. This demonstrated Ed Leedskalnin's perpetual motion holder effect. Conclusion: there is something moving inside the core and the core has zero resistance to that flow. Let's call the flow magnetic current. I then put 3 identical coils on the core, one had a load connected to it and the others were left unconnected. I applied AC to the primary. There was same voltage at both output coils. Short-circuiting one output coil caused power to begin to flow in the primary, and at the same time voltage dropped to half in the unconnected output coil. The following, seemingly unimportant and obvious conclusion can be made. Conclusion: a secondary coil also creates magnetic current and different secondary coils affect each other in opposite ways. Next, I connected various points in the core with iron. Points that I used for testing are shown here. Figure 1. EI core with coils and probe points. When iron was connected between points 1 and 2 there was no effect. When connected between points 2 and 3 there was a notable effect. a sound and sort of vibration when iron approached the core, which ceased when both ends touched the core. When connected between points 4 and 5 there was the same effect but stronger. In this case power output of the core dropped while power input remained the same. Conclusion: magnetic current inside the core wants to loop back to itself through every possible route it can. For the next test I used a nano perm core, and I wound coils of about 50 turns for both the primary and the secondary. The primary was fed with AC from the output of an audio amplifier and the secondary was connected to a loudspeaker. I then played some music from my PC through the audio amplifier. I heard the music and higher frequencies were attenuated while lower frequencies sounded fine. What I had got was a low-pass analog audio filter. Conclusion: there can be all frequencies active in the output coil at the same time. Hence there can also be magnetic current active at the same time at all frequencies in the core. Based on these simple tests I then reached the following overall conclusion: in a closed-loop core there can be a flowing magnetic current which varies with time when the core is energized using AC electric current. The magnetic current has summing/subtracting properties and it also has a perpetual motion property. It can be modeled as a sine wave and sine waves can be manipulated to our advantage. Using two coils in a resonant LC circuit. Below are pictures of CI-shaped and EI-shaped cores which show how coils should be wound. All coils are wound in the same direction and connected from the ends. When coils are used like this, their closed-loop magnetic currents cancel each other and only a local inductance field remains. This is why there is a resonant frequency but much higher than otherwise possible. For example, I used two 160 turn coils and resonant frequency was between 12 and 13 kHz. One coil of 20 turns in my nano perm core blocks everything above 1.5 kHz. And I can push 260 watts from my audio amplifier. Figure 2. CI and EI resonance setup. Now you may think that this is of no use. If there is a power collection coil then it will not collect anything as magnetic currents inside the core are cancelled. But if these two coils are used as outputs and they are driven by a primary coil which is wound over both of them, then the result is that power is generated. Both outputs will then be in exactly the same phase and when connected correctly they amplify each other while the primary circuit does not see a thing as the opposing phase magnetic currents cancel each other out. See Figure 3. Figure 3. CI and EI with primary on top. The primary coil is in fact a solenoid, it has no magnetic loops and it has low inductance. Secondary coils form closed loops and they have higher inductance. The more secondary coils which are used, the more magnetic current, in correct phase, will be circulating inside the core. Don Smith called this resonant magnetic flux. Thick multi-strand wire, not Litz type, should work best, few turns and a capacitor. But any thickness of wire will do. Warning: begin using small diameter wires, something below 0.5 mm. I haven't tested thick wires but resonant rise will occur. Also, you had better start with low-Q resonant circuits as you don't want kilovolts generated near you. Tuning is now easy. First you make a parallel LC circuit using secondary coils, see Figure 2. For the core you can use a toroid shape, CI or EI core pieces. The EI shape pieces should be the most efficient. Next find the resonant frequency of the LC circuit which you have just created. Now disconnect the secondary coils and do the same for your primary coil. Adjust the number of turns in the primary coil or amount of capacitance until you get a close enough resonant frequency in the primary matching with the secondary coil's resonant frequency which you have just found. Now connect the load and feed the primary coil with a pure AC sine wave. Pulses do not work because a square wave pulse contains all frequencies which in turn creates magnetic currents at all frequencies resulting in a total mess of magnetic flow inside the core. The input definitely has to be a pure sine wave. There has got to be amps running in the primary LC circuit so that the primary capacitor is filled. If you get resonance but see no power, then try using a higher frequency. If you use EI or CI type cores, make sure that there are no air gaps between the pieces forming the core. There has to be a closed magnetic circuit in the core. Using an LED as a load obviously does not work because it prevents resonant rise in the output LC circuit. I suspect that EI works best when core dimensions are such that the core area in the middle leg is twice that of the outer legs. Magnetic currents created by the secondary coils should be equal so that their sum is always zero. Permeability of the core does not matter, and you can use iron or ferrite. You need to use a frequency that is within the limits of what the core material can handle. The nanoperm material which I used can handle frequencies up to 1 MHz. 5. My results. My input source was an audio amplifier. I expect that it outputs power at 5 volts, but I really don't know. I cannot measure it as I have no meters. I used the Goldwave audio editor to create a sine wave input. It has a nice expression evaluator that allows you to do frequency sweeps easily. Goldwave is a free software download available from www.goldwave.com. I used AM088 nanoperm core from Magnatech. Permeability was 80,000, with 0.3 mm wire. First I had about 160 turns in each secondary and 20 meters wrapped in the primary, about 120 turns or so, far too much, but that was my initial guess. I had to use high number of turns because my input was limited below 20 kHz. I was lucky to find suitable L and C combinations so I could see a glimpse of the resonant action. Since I don't have any meters, I used halogen bulbs. I put a 5 watt 12 volt bulb in the primary and 10 watt and 8 watt 12 volt bulbs in the output. I did a sweep, and as the frequency went through the sweet spot, output power increased. At resonant frequency somewhere between 12 kHz and 13 kHz there was no light at all in the primary halogen, but both of the output bulbs were lit to about half brightness. Now that I got it, I reduced the number of turns in the secondary coils to half and changed the capacitance from 440 nanofarads to 1000 nanofarads. The resonant frequency at the output changed a bit, but since the resonant area was wide it did not make a notable difference. Now I got more light, almost full brightness, and halogens were way too hot to touch. Again, no light visible in the primary side bulb. So what did I just do? DC resistance dropped to half in the output coils, so their Q factor was doubled, giving double the resonant rise in the output LC circuit. Cool. I observed the same action in the primary LC circuit. There I used 40 meters of wire in the primary and I got much less power output. In that case the Q factor dropped to half, which explains the results nicely. 6. Things to try after a successful replication. Bifilar windings should lower the total value of L, and so a higher resonant frequency can be used. At the output there could be bifilar windings without capacitors because high voltage capacitors are expensive and dangerous when loaded. Then place a correct capacitor in primary LC circuit to tune in.